Hello everyone, my name is Anthony Schuler, and today I will be discussing my final project titled Time Series Techniques for Home Price Index Modeling. Every month at the national level and various metropolitan levels, S&P Case-Shiller home price indices are calculated and reported by CoreLogic, a U.S. financial information company. The index tracks repeat sales of homes by making monthly comparisons based on the number of homes sold. In general, the index provides a snapshot of market changes in home prices. For this study, analyses focused on the S&P Case-Shiller Illinois-Chicago Home Price Index. Data was obtained from the FRED website, a collection of economic data managed by the Federal Reserve Bank of St. Louis. Data was collected in the non-seasonally adjusted form between January 1987 and July 2017. A total of 397 instances, i.e. monthly index values, were collected. The goal of this study was to develop a model that both adequately describes the time behavior of the S&P Case-Shiller Illinois-Chicago Home Price Index and produces accurate forecasts for future values of the index. If successful, the resulting model could be used as a tool for home buying. Prior to fitting any model to the data, some initial exploratory analysis was done to better understand the time series. First, a histogram and QQ plot were created from the raw index data to visually check for normality. Based on the plots, it appears as though the series is not made up of completely normally distributed data. First, the histogram appears to show more of a bimodal than normal distribution. Second, the data points on the upper and lower ends of the QQ plot stray from the red center line, indicating abnormal distribution tails. Expanding on the visual assessment of normality, a series of statistical tests were also performed. These tests included a test for skewness, kurtosis, and the Jacques-Barré test for normality. For the kurtosis and Jacques-Barré tests, significance was determined at the 0.05 alpha level. In all cases, the results of the tests indicate non-normal data. Here, we see that the distribution is slightly right-skewed, has thin tails, and is not normal. Next, the raw data was converted to a time series object and plotted. In analyzing the time plot, and supported by the normality assessment discussed previously, it becomes pretty clear that the time series is not stationary. Not only does the series show a positive linear trend over all time, indicating non-constant mean, it also shows non-constant variance. In particular, the amplitude of very subtle cyclical/seasonal spikes between 1987 and 2000 is smaller than that of the much more noticeable cyclical/seasonal spikes between 2008 and 2017. Moreover, from 2000 to 2008, we also see a drastic increase in index followed by a sharp decline, a result of the financial crisis of 2008. Continuing with the visual assessment of stationarity, the lag-K autocorrelations were plotted for the time series. Not surprisingly, the ACF plot indicates a non-stationary time series. Here, the ACF values decay very slowly and have not reached zero even after 50 lags. As such, the series may require differencing and/or seasonal differencing to make it at least weak stationary and acceptable for modeling. Note also that a series of augmented Dickey-Fuller tests, not pictured here, also supported the need for differencing. Despite first differencing, the trend exhibited by the ACF values in the left figure still does not appear to indicate a stationary series. However, the plot does exhibit seasonality, as evidenced by the alternating clusters of ACF values significantly different from zero. Here, the positive significant ACF values tend to occur around lags 1, 11, 12, 13, and their various multiples. For example, 23, 24, and 25. The negative significant ACF values tend to occur around lags 5, 6, 7, and their various multiples. Based on these observations, it appears as though the data exhibit monthly seasonality. In analyzing the right figure, the ACF values decay relatively quickly to zero after about 6 lags, and then stay at zero or nearly zero for most of the subsequent lags. Furthermore, a series of augmented Dickey-Fuller tests at different lags support the assessment of weak stationarity. All tests rejected the null hypothesis at a 5% significance level with p-values of less than 0.01. Ultimately, after applying monthly seasonal differencing, it appears as though the series is now at least weak stationary and suitable for modeling. Based on the results discussed in the exploratory analysis slides previously, and in particular the apparent presence of seasonality, a number of SARIMA models were fit to the data. To do this, R's AutoArima function was used with the settings specified on the slide. Based on lowest BIC, we see that the SARIMA 212, 101, 12 model performed best, but not by much. All three models had very similar BIC values, and as such, all three will be compared in the subsequent slides to help determine which model is truly best. In order to assess the adequacy of the top three models presented previously, each model was subjected to a series of diagnostic tests. First, R's COEF test function was applied to each model to determine whether or not its coefficients were statistically significant at the 0.05 alpha level. Ultimately, the results of the test showed slight differences between models. Model 1 had all but one coefficient, i.e. the first autoregressive coefficient, AR1, significant at the 0.01 alpha level at least. Model 3 also had all but one significant coefficient, i.e. the AR1 coefficient, this time at the 0.05 alpha level at least. Model 2, on the other hand, had two insignificant coefficients, the AR1 and AR2 coefficients. While insignificant coefficients aren't desirable, they do not mean that the resulting model is useless. Next, each model was subjected to a residual analysis. The purpose of the residual analysis was to determine whether or not the residuals of the model were independent and identically distributed, or white noise. In other words, the residual analysis lets us know that the residuals are not correlated. If the residuals are correlated, the model is unlikely to generalize well. The first step of the residual analysis was the creation of histograms and QQ plots to be used for visual assessment of the normality of the residuals. Although only one set of plots is pictured here, a similar trend exists for all three models. The histograms appear to show a relatively normal distribution, while the QQ plot indicates possible issues with tails. To confirm these suspicions, each model then underwent a series of statistical tests to further assess normality. These tests are the same as those discussed in the exploratory analysis slides previously and should be interpreted in the same way. For the kurtosis and Jark-Barrett tests, significance was determined at a 0.05 alpha level. Not surprisingly, the results of the skewness, kurtosis, and Jark-Barrett tests all suggest that the residuals for each model aren't normally distributed. However, the histograms and QQ plots aren't grossly abnormal, and the skewness and kurtosis values aren't very large, so the residuals can be considered normal enough to proceed. Lastly, each model was subjected to both a visual and statistical check for autocorrelation of the residuals. Here, the visual check for correlation is the ACF plot, and the statistical check is the Young box test. Fortunately, the ACF plots and Young box tests yielded promising results. Although only one plot is pictured here, all the ACF plots, in general, suggest that the residuals are white noise, or nearly white noise. Outside of a couple legs for each model, the ACF values for most legs are not significantly different from zero, i.e. their values fall inside the dashed blue lines. As a whole, the ACF values for the residuals decay quickly to zero and stay there as the lag increases. Additionally, the results of the Young box test also suggest that the residuals are white noise. All models, for all legs tested, fail to reject the null hypotheses of zero autocorrelation. Furthermore, the stationarity of each model was also checked using a simple plot of the inverse or characteristic roots of the models. Although only one plot is shown here, all inverse roots for all three models lie inside the unit circle. As such, each model represents a stationary process. These results, in combination with the results of the coefficient significance test and residual analyses, suggest that the models are adequate for describing the time behavior of the S&P Case-Shiller Illinois-Chicago Home Price Index. In assessing the model diagnostics results, it becomes apparent that all three models are quite similar. The results of the COEF test function, residual analysis, and stationarity check were comparable for all three models. As such, forecasting was used to help shed some light on the best model of the three. First, forecasts for the next 24 months were computed and plotted. By doing this, one can visually assess how well the forecasts mimic, or don't mimic, the behavior of the original index data. Not surprisingly, the forecasts for all three models, i.e. the blue line, show similar behavioral trends. In particular, the forecasts match the up and down fluctuations of the original time series data between 2008 and 2017, i.e. the black line. However, the amplitude of the fluctuations for the first and second models appears to be slightly greater than that of the third model. In this case, the greater amplitude of the first and second models appears to align a bit more closely with the amplitude of the original data. To gain even greater insight into the forecasting abilities of the models, a backtesting procedure was applied to each model to determine the accuracy of its forecasts. For backtesting, approximately 85% of the data was used for training and 15% was used for testing. While the backtesting procedure calculates several different accuracy metrics, the metric of focus for this study was mean absolute percentage error, MAPE. In terms of MAPE, we again see very similar performance across all three models, with a very slight edge going to the Surima 212-10112 model. Here, an MAPE value of approximately 0.0037 means that on average, the forecasted values deviate from the true values by approximately 0.37%. Based on the model diagnostics and model forecasting results, the Surima 212-10112 model was determined to be the best of the three models analyzed. In comparison to the other models, this model stood out, albeit barely, in a few key areas. First, this model had only one insignificant coefficient, and of the coefficients that were significant, all were significant at smaller alpha levels than the other two models, i.e. 0.01 as compared to 0.05. Second, this model had the lowest BIC value at 696.544. Third, the forecasts from this model mimicked the behavior of the original time series as good or better than the other two models. And finally, this model produced the lowest MAPE value at 0.00374, indicating strong forecasting ability. In conclusion, it is clear that the overarching goal of the study has been met. The models developed in this study, and in particular the SARIMA 212-10112 model, produce accurate forecasts that reflect the time behavior of the S&P Case-Shiller Illinois-Chicago Home Price Index. As such, the equation for the SARIMA 212-10112 model shown on the slide can be used by prospective home buyers as a tool to identify future trends in home prices for the Chicago, Illinois metropolitan area.